Namaste and welcome back to the lecture on linear algebra through geometry. In the previous lecture, we looked at the idea of vectors in 3D. We looked at how do we combine vectors in 3 dimension. We looked at the notion of scalar multiplication and vector addition. Then we said linear combination of vectors. Then we also defined the idea of linearly independent set of vectors, dependent set of vectors. From our knowledge of 2D, we know that if one vector is a multiple of the other, we say that they are linearly dependent, and in case of 3D you may have a third vector coming into picture, and when you have the third vector, then if you look at the set of 3 vectors, you call the set of 3 vectors to be linearly dependent if one of them can be expressed as a linear combination of the other two. Otherwise, the set of 3 vectors are linearly independent. And we also looked at the idea of length of a vector, which had similar which had a straightforward what do you call definition, or right, like what we had in 2 dimension. We used Pythagoras theorem to get the length of the vector. Here also in 3D, if you have a vector in 3 dimension, you could get the length of the vector as square root of the individual components, the sum of individual components squared. That means you have a vector u which has 3 components u1, u2, u3, then the vector of the length of the vector u is basically square root of u1 squared plus u2 squared plus u3 square, which we actually interpreted in terms of the dot product, which is square root of u dot u. And the moment the dot product came into picture, we also said that we could find out if the angle between the 2 vectors is 90 degrees. That means if the dot product is 0, we said that the 2 vectors u and v are orthogonal to each other, and if not, you can actually find out the angle between the 2 vectors as cos theta is equal to u dot v by the product of the length of the 2 vectors u and v. And towards the end of the last lecture, we said that okay, where are we heading from, the idea of dot product and stuff. So we are going to look at how do we define planes passing through the origin, lines passing through the origin, what is the projection of a vector onto a line passing through the origin, what is the projection of a vector onto a line passing through the origin, and we get to the idea of cross product from there. So in this lecture, we will look at the idea of defining a line passing through the origin with respect to a vector which is orthogonal to this, and we are going to look at defining a plane passing through the origin in terms of a vector which is orthogonal to the plane, and we are going to look at the projection of a given vector onto a plane passing through the origin, onto a line passing through the origin, and we will go ahead with finding out the area of a parallelogram which is formed by 3 component vectors or 2 vectors in 3D and so on, right. So let us get on to the lecture. So what are we going to look at? Recall that if u dot v is 0, we said u and v are orthogonal to each other. The vectors u and v are orthogonal to each other. Which we denote it as u, the vector u is orthogonal to the vector v. That is the notation that we use, right. Now what are we going, and from there we said that okay, we are going to look at if u dot v is not equal to 0, then you can always find out the angle between the 2 vectors as cos theta is equal to the dot product of the 2 vectors divided by the product of their lengths. And you know that again, if u dot v is 0, cos theta is 0, therefore theta is 90 degrees and so on. So you can find out the angle between the 2 vectors. So what are we going to do from now? So what we are going to do is we are going to look at the projection. We are going to look at the projection of a vector u on to another vector say v. We are going to look at the projection of a vector u onto another vector v. So, suppose we have this, suppose u is a vector 3 component vector, suppose u is equal to u1 u2 u3 and v is another 3 component vector say v1 v2 v3, then let us look at this like. So, basically we are looking at 3 dimensions. So, let me take 3 axes. So, we have this to be my x1 axis or the direction along E1, this is the direction along E2 and that is the direction along E3. So, I have these 3 vectors E1, E2, E3. Now, what am I going to do? I am going to draw this vector u. The vector u, let me take it this way. Let us take this to be the, okay, just a minute. Okay, what we do is let us take let this be the vector u, right, and what we are going to do is we are going to look at another vector v, which is basically you are going to look at a sorry. So, we are going to have another vector v along this direction, it is a let us take this to be the vector v. That means, you are going to have a line passing through the origin along the direction of v. So, this is the vector that I am going to have. So, what am I going to do? I want to project this vector u onto the direction of v, onto the vector v. So, how is it going to look like? So, this is going to be the projection. So, what is this going to be? This is going to be the vector, this is going to be the vector, let me call this as let us say p of u, which corresponds to the projection. So, let me write this properly. So, we are going to have this as, this is going to be this. So, we are going to have p of u, the projection of vector u along the direction of v to be a multiple of this vector v, right, to be a multiple of this vector v. So, what we see is, it is interesting that if you remove this projection of the vector u along the direction of v, whatever is left with us is basically the component which is say u minus t v. So, let me write this. So, this is going to be the component u minus t v, and this u minus t v is orthogonal to the vector which is v. So, what we have, this is going to be again 90 degrees, this is our parallel vector. So, what are we going to say? We are going to say that okay, let us write this. So, projection, we already did this, projection of the vector u onto v is that multiple of v, is that multiple of v t v, let us say t v, where t is the scalar, such that we have u minus this t v, what are we going to say, is going to be the component u minus t v is orthogonal to the vector v, orthogonal to the vector v. Now, what does that mean? That simply implies the vector u minus t v dot v is going to be the scalar 0. We know that the dot product is going to give us a scalar, and that is going to be 0. So, what are we going to do? We are going to look at this. So, what we see is, you see that it is u dot v minus t times v dot v is equal to 0, and therefore, what we see is we see that t is equal to the scalar t is equal to u dot v divided by v dot v. Is that okay? So, we have this to be u dot v divided by v dot v. So, therefore, the projection, the vector that we are going to get, this is the scalar value. So, we are going to get the projection of u onto v is given by p of u is equal to u dot v divided by v dot v. We say that it is in the direction of the vector v, right. So, what is this basically, what does this projection p of u, what does that imply, what does that actually mean? So, we are going to write that. So, we are going to say that this multiple of t v, what this multiple of the vector v. So, this is the multiple of vector v, this is the multiple of v that best approximates u. The thing is, where are we going to use all these facts, this interpretation and stuff? We will see that when you try to solve a system of equation, you end up getting the situation where you have no solution, you have to find out the least squared solution. So, we will look at that idea of least squared solution, wherein which we are trying to look at the best approximate of a vector b of a vector onto the what we call as the column space, which we will do in subsequent lectures. Okay. Okay. Now, so we found out the projection of this vector u along the direction of v. We tried to find out the projection of the vector onto the line which passes through the origin in the direction of v. That is exactly what we have done. Now, what we are going to do is we are going to look at the projection of a vector, of a given vector onto a given plane that passes through the origin. So, let us look at that. So, projection of a given vector let us call that vector say x onto a plane passing through the origin. So, that is what we are going to look at. So, this is what we are going to look at. So, what we do is let's look at this. So, let u be this vector, say u1, u2, u3 be a non-zero vector and let us call the plane that passes through the origin and orthogonal to u to be the plane p pi. So, let p pi be the plane passing through the origin, and orthogonal to u. Orthogonal to the vector u. Let us take let y be any vector on the plane, let y equal to y1, y2, y3 be a vector on the plane p pi, in the plane p pi. Now, since this vector y lies in the plane, the vector y and the vector u, they are orthogonal to each other because the plane is orthogonal to the vector u. Therefore, what we are going to say, since y is on p pi, since y is in the plane, p pi, and p pi is orthogonal to u, we have orthogonal to u, we have u dot y is equal to 0, which implies you are going to say that y 1 u 1 plus y 2 u 2 plus y 3 u 3 is equal to 0, and that defines the plane p pi passing through the origin and orthogonal to the vector. So, this is basically the equation of the plane p pi. Equation of the plane p pi. Now, what we want to do is let us look at it like how let us have a look at how things are. So, I have this, I have the coordinate axis, and let me take this to be the plane p pi, this is the plane p pi. What I am going to do is I am going to have a vector orthogonal to p pi, and that I am going to define it as the vector u. So, let this be the vector u, and I am going to look at another vector x. So, let us take this to be the vector x, right. So, what I want is I want to look at the projection of this vector x onto the vector onto the plane p pi. So, let us take this. So, this is basically my vector x. So, what are we going to look for? We are going to look at the vector x. Let x be a vector. We define this basically, okay, let us assume that this is the plane, just a minute. So, let us assume that this is the plane that we have, and let this be q of x, that is the projection of the vector x onto the plane. So, let q of x be the projection of x onto p pi, the plane p pi, right. Basically that is the foot of the perpendicular from x to, let us say, the plane p pi. So, this is basically q of x is the point, this is basically the foot of the perpendicular from x to p pi, right, and that is what we are going to call that as q of x. Okay. Now, what we know is this perpendicular that we have drawn, which is from the vector x to q of x, it is perpendicular to the plane p pi, and we see that it is also parallel to the vector u. So, what we are going to say, since the line segment joining x and p of x, I mean x and q of x is perpendicular to p pi, and we also know that u is perpendicular to p pi, because that is how we have defined, and we know that u is also perpendicular to p pi. We conclude that we have the vector x minus q of x, which is the projection x minus q of x, is parallel to the vector u, is parallel to the vector u, which means I can write this as x minus q of x is equal to say some t u, right. We are going to write this as t u, or which is the same as saying x minus t u is equal to q of x. Now, where is q of x? Q of x is basically on the plane p pi, is that right? The q of x is in p pi, q of x is in p pi. Therefore, we also see that x minus t u, x minus t u, if we do it here, so this is going to be the vector t u. So, we have along this direction we have this vector t u. So, we say that x minus t u is perpendicular to u, x minus t u is perpendicular to the vector u, right. It is perpendicular to the vector u, right. That implies t u is the projection of x onto u. It is the projection of the vector x onto the line in the direction of u, I will say onto the vector u, right. So, what do we get? In turn we get x minus q of x is equal to t u is what we had, that is nothing but the projection of this vector x onto the u, where p of x is the projection of x onto u. Onto u, and thus we see that x minus p of x, thus we see that q of x is equal to x minus p of x is the projection of the vector x onto the plane p pi passing through the origin and orthogonal to the vector u. Right. So, how does this basically look like? We have already seen it diagrammatically that x minus p of x is going to be the projection of the vector x onto the plane p pi, which is passing through the origin and orthogonal to u. Now, having found the projection, now the question that we ask is what is the distance from the point x to the plane p pi. So, the question we have right now is this question: what is the distance from the point x to the plane p pi. Right. So, let us look at this. So, what are we trying to ask? We are asking what is going to be this distance. This is the distance that we want to calculate here, that is the distance that we want. So, how are we going to do it? So, let us redraw this again and then check. So, let us do this. We have the coordinate axis and we had the plane, this is the plane p pi, this is the plane p pi we had, and we had this we had this vector u and vector x. Let us look at that. So, we have this vector u. Let us take this to be the vector u. This is the vector u that we have. We have this to be the vector x, and the perpendicular dropped from this to the plane. Let us call this as q of x, and this basically p of x. That is the projection of x onto this, the vector u. So, what we want is we want to find out the distance between this point x to the plane, which is exactly the length of the vector, which is basically the length of the projection of this vector x onto the direction of u. So, what we say is the distance. So, the distance between x and the plane p pi is precisely the length of the projection p of x, the length of p of x, right. So, what is that given by? So, what is that? The length of p of x, we already know that it is basically x dot u. This is basically absolute of x dot u divided by u dot u into the length of this vector u. So, which is nothing but we have absolute of x dot u, and that is the length of vector u, and we know that u dot u is nothing but u square. So, we are going to have this length square. So, we see that this and this gets knocked out. So, what we have is absolute of x dot u divided by the vector length of u. So, the distance d is given by d is equal to absolute of x1 u1 plus x2 u2 plus x3 u3 divided by square root of u1 square plus u2 square plus u3 square. So, that is the distance from the point x to the plane p passing through the origin and orthogonal to the vector u. Now, the next question that we ask is what is the distance from the point x to the line passing through u along the vector u. Now, why do we do all these things? These things help us when we try to calculate the area of the parallelogram formed by two linearly independent vectors in 3D. This will help us calculate the area, and this distance whatever d that we have calculated will help us calculate the volume of the parallelepiped when we look at three linearly independent vectors in 3D. So, we will go towards that. So, what is the distance from the point x to the line along the vector u? I will say the non-zero vector u, non-zero vector u. So, how does that how do we look at that? So, basically I have this, let me again draw the coordinate axis and let me have my vector u. So, let us say this is the vector u that I have, and let us take another vector, let us say x, this is the vector x, and we want to find out this distance. So, this is basically the projection of that vector x along the direction of u. So, this is basically the distance is nothing but the length of the difference vector, which is nothing but x minus p of x, the length of this. So, the distance is given by, so this is nothing but the distance is equal to the length of the vector x minus p of x. P of x is the projection of x onto the direction of u. So, what I have now, we know that already from the idea of projections, we know that x minus p of x is orthogonal to p of x, is orthogonal to p of x. So, I can use Pythagoras theorem and say that the squared length of x minus p of x is equal to x squared minus p of x the whole square. And what is that? X squared is basically x dot x minus p of x is nothing but x dot u divided by u dot u, right. It is going to be the whole square divided by u dot u. I mean, if you can actually simplify this, it is easy to figure out that this is basically u dot u in the direction of u dot product with itself dot, that is a vector, dot product with itself. So, we get x dot u divided by u dot u in the direction of u. So, if we simplify this, we get the squared length of this is nothing but square root of x dot x into u dot u minus x dot u the whole square, the whole thing by the vector length of u, right. That is going to be the so that is going to be the, this is going to be x. So, the length of x minus p x is basically the square root of x dot x into u dot u minus x dot u the whole square divided by the vector length of u, right. So, that is the distance. So, this is basically the distance that we are looking for, distance from point x. This is basically the distance from x. X to line through u. Okay, that is the distance from x to line through u. Now, what do we want to find out? We want to find out the area of a parallelogram, which is basically, it is easy to figure out what is the area of a parallelogram. Area of a parallelogram whose sides are, let us say, x and u. Parallelogram with sides along x and u basically this. So, we have this, let us assume that this is the vector u, and let us assume that this is the vector x. Now, we know that the parallelogram is formed by doing this. The parallelogram is basically formed by this. So, we have this to be the x vector. We want to find out the area of this. Area is nothing but base into height, where base is basically the vector length of u, and the height is nothing but, this is exactly what we found in the previous a couple of minutes back. This is basically the height that we have, and that height is nothing but square root of x dot x into u dot u minus x dot u the whole square divided by vector length u. Therefore, the area of the parallelogram is given by area is nothing but square root of x dot x into u dot u minus x dot u the whole square, right. So, this is going to be the area of the parallelogram. Now, having found the area of parallelogram, now we are going to look at something more which we will see in the next class. We are going to define the idea of cross product, and we see that we will see that the area of this parallelogram is basically the length of the cross product, the vector that you get out of doing a cross product. We will define what cross product and all those things in the next lecture. Thank you.